Offshore oil and gas are vital resources. They lie hidden beneath the world's oceans. Humanity's thirst for energy drives this search. We drill deep into the seabed. This quest powers our modern civilization. It also fuels economies globally. Accessing these reserves is a great challenge. It requires immense effort and innovation. Drilling offshore is unlike drilling on land. The marine environment presents unique obstacles. Water depths can be extreme. Weather conditions are often harsh. Storms and currents pose constant threats. Specialized equipment is absolutely essential. Highly skilled personnel are also needed. The costs are significantly higher. The risks are greater too. This brings us to specially designed wells, or SDLs. These are not ordinary wells. They are engineered for complex offshore tasks. SDLs often involve intricate well paths. They might reach multiple reservoir targets. This is done from a single surface location. Such wells are crucial for efficient development. They help unlock challenging subsea fields. The purpose of SDLs is multifaceted. They aim to maximize hydrocarbon recovery. They can reduce the overall drilling footprint. This minimizes environmental impact. SDLs also improve project economics. They allow access to otherwise unreachable reserves. These wells represent advanced engineering. They are a cornerstone of modern offshore strategy. This is key for IGTA students to grasp. Offshore drilling relies on massive structures. These are called mobile offshore drilling units, or MODUs. They are floating factories with all drilling equipment. They also accommodate the crew. MODUs can move to new locations, vital for exploration. In shallow waters, jack-up rigs are common. They have extendable legs that reach the seabed. For deeper waters, semi-submersible rigs are used. They float on large pontoons for stability. Drill ships operate in extreme depths, using advanced technology. The offshore drilling lifecycle has several stages. It begins with the exploration phase. This is the initial search for oil and gas. Geologists and geophysicists lead this effort. They look for signs of hydrocarbons. These signs are hidden beneath the ocean floor. This phase is filled with uncertainty. It is a high-risk, high-reward endeavor. Exploration employs sophisticated techniques. Seismic surveys are fundamental. Ships tow arrays of sensors. These sensors send sound waves downwards. The waves reflect off rock layers. Computers process these reflections. They create images of the subsurface. Geologists interpret these images. They identify potential hydrocarbon traps. These traps might hold oil or gas. If exploration shows promise, appraisal follows. This phase aims to confirm the discovery. An appraisal well or wells are drilled. These wells test the reservoir directly. They gather crucial data. This includes the size of the discovery. It also includes reservoir rock properties, and the type and quality of fluids. This information is vital. The appraisal phase leads to a critical decision. Is the discovery commercially viable? Does it contain enough oil or gas? Can it be produced economically? All data is carefully analyzed. Engineers assess development options. If positive, the project moves forward. If not, the area may be relinquished. This is a pivotal moment. Once a discovery is deemed commercial, development begins. This phase involves extensive planning. Engineers design the field development strategy. This includes the types of facilities needed. Production platforms might be installed. Subsea systems are often required. These systems sit on the seabed. Pipelines are planned to transport products. Drilling development wells is a major part. These wells are carefully planned. Production wells bring hydrocarbons to surface. Injection wells might also be drilled. These help maintain reservoir pressure, or they dispose of produced water. Well placement is optimized using models. This ensures maximum recovery. The goal is efficient extraction. Next comes the long production phase. This is when oil and gas flow. Hydrocarbons travel from the reservoir. They move up the wells to the platform. On the platform they are processed. Oil, gas, and water are separated. Impurities are removed. The oil and gas are treated. They must meet sales specifications. Finally, the processed oil and gas are transported. Pipelines often carry them to shore. Sometimes tankers are used instead. This is common for remote offshore fields. The products reach refineries and markets. Production operations are continuous. They require constant monitoring and diligent management for many years. This ensures safe and efficient output. Section 5. Blueprint for black gold. Well planning, design, and drilling. Meticulous well planning is paramount. It is the first step before drilling. Planners define clear well objectives. They identify the target reservoir zones. Detailed geological and geophysical data are used, potential risks are thoroughly assessed, cost estimates are carefully prepared, contingency plans are also developed. This ensures readiness for surprises. Well design follows the planning stage. This is a highly technical process. Engineers design the casing strings. These steel pipes line the well bore. The well trajectory is carefully plotted. This is especially true for complex SDLs. The drilling fluid or mud program is designed. The cementing program is also critical. Safety systems are incorporated throughout. The drilling operation itself is complex. It is where the plan becomes reality. Most offshore wells use rotary drilling. A drill bit grinds the rock. The drill string rotates the bit. It also provides weight. The drill string consists of many sections. These sections of pipe are added. This happens as the well gets deeper. Several key operations occur during drilling. Mud circulation is continuous. The drilling mud cools the bit. It carries cuttings to the surface. It also controls downhole pressure. Casing strings are run into the hole. They are then cemented in place. Cementing provides zonal isolation. It prevents fluid migration. Pressure control is always a top priority. Section 6. Maximizing flow and saying goodbye. Enhanced recovery and abandonment. Initial production relies on natural pressure. This declines over time. Flow rates decrease. Intervention is necessary. Operators boost production. Artificial lift techniques help. Gas lift lightens the fluid column. ESPs push oil upwards. Enhanced oil recovery extracts more oil. Water flooding sweeps oil. Eventually fields are abandoned. Wells are permanently plugged. This prevents leaks and protects the environment. Offshore facilities are decommissioned. The seabed may need restoration, all under strict regulations. Section 7. Guardians of the deep safety environment and regulatory waters. Offshore operations carry inherent risks. The environment is exceptionally harsh. Workers face storms and remote conditions. Operations involve high pressures. They also handle flammable hydrocarbons. A strong safety culture is essential. It must permeate every level of activity. Protecting people is the highest priority. This cannot be overstated enough. Robust safety management systems are vital. These systems identify potential hazards. They assess the associated risks. Comprehensive emergency response plans are developed. Regular drills ensure preparedness. Extensive training is provided to all personnel. Personal protective equipment or PPE is mandatory. These measures reduce accident rates. They save lives in critical situations. Environmental protection is a major concern. The potential for oil spills is serious. Such spills can harm marine ecosystems. Operators must implement strict safeguards. Waste management is carefully controlled. Emissions to the air are monitored, and they are minimized where possible. Protecting the ocean is a responsibility. This industry takes it very seriously. A complex regulatory framework governs operations. National governments issue licenses and permits. International laws also apply. Environmental impact assessments are required. These studies precede any new development. Regulators monitor compliance closely. They enforce rules vigorously. This ensures responsible resource extraction. It holds companies accountable. Section 8. Horizons Anew. Offshore technology, challenges, and the future outlook. Technology in offshore drilling is ever evolving. Recent advancements are transforming the industry. Automation is reducing human exposure. Robotics perform hazardous tasks. Digitalization connects all operations. Big data analytics optimize performance. Improved seismic imaging reveals deeper secrets. These tools enhance efficiency and safety. Advanced drilling techniques are now common. Managed pressure drilling, or MPD, allows better control. It is used in challenging wells. Extended reach drilling, or ERD, accesses distant targets. This is done from existing platforms. Complex well paths are now achievable. This includes multilateral wells. These innovations unlock more resources. They push the boundaries of what is possible. The industry faces significant challenges. High operational costs are a constant factor. Oil price volatility impacts investment. Geopolitical events create uncertainty. The global energy transition is underway. This means a shift towards cleaner sources. Public perception of fossil fuels has changed. These factors shape the industry's path. Despite challenges, the future outlook is dynamic. Global demand for oil and gas continues. It will remain significant for decades. The focus is on greater efficiency. Sustainability is also a key driver. The decommissioning market will grow. This is as old fields retire. Offshore expertise can aid new energies like offshore wind and carbon capture.